looking at section 2.6, rational functions and their graphs, looking at part 2. So in this section, we're going to look at using transformations to graph rational functions, graph some rational functions, and then not quite today, but in the next lesson, so kind of a part 3, we will eventually get to looking at identifying some slant asymptotes and then also solving some applied problems involving rational functions. So we kind of have a part 2 and part 3, but for today is just part 2. So what does it look like if we have a reciprocal function? So it talks about the basic reciprocal function, a flipped fraction, right? So if we have f of x is equal to 1 over x, if we take a look at that graph, we can kind of identify we have, again, anytime you have some sort of function that you do not know what it looks like, you can always make a table of values, plug in some numbers for x, figure out what you end up for y. So for instance, if you were to plug in a 1 for x, you'd have a 1 over 1, which is 1. So we'd have this ordered pair here, 1, 1. If I plugged in a 2 for x, we'd end up with a 1/2. So over at 2, we're up at 1/2. If I would have plugged in a 1/2, a 1 divided by a half would have ended up giving us 2. So if I took one apple and I divided it by halves, I have 2 pieces, 2 parts, right? So that's what that part is looking like in the positive. So this graph here, it's kind of approaching this y-axis, and it's going to continue to grow and grow and grow, but never touch that axis. It's never going to touch 0. And same thing's going to happen with our going off to our infinity off to the right hand side. That's going to continue to approach the x-axis, but never actually make it to 0. If you were to look at the opposite version of that, plugging in some of those negative values, you can kind of see that same type of pattern that's happening on the other side. What type of symmetry is happening? We start seeing some origin symmetry. Remember, we kind of talked about looking for how things kind of relate. We have even functions, we have odd functions. This would end up being an odd function, meaning that the value of our function at negative x is the same thing as the opposite of our function. And then if we look at the other graph we have here, the other reciprocal function that has the f of x is equal to 1 over x squared, that is going to look kind of almost like they took a parabola. If you think about a parabola, your U-shaped graph, it's almost like they split it in half and they kind of flipped it outwards. So it ends up like that. That's kind of how that looks. So it's almost like they took that U-shaped graph and they kind of split it outwards. And so what happens here is you kind of have some similar characteristics. These lines or these curves are going to continue going towards infinity, but it's never going to touch that y-axis on either of those sides. It's going to get as close as it can, but never touch. And then same thing with the x-axis. It's going to approach that x-axis, but it's never going to hit the x-axis. So we're going to also have some asymptotes in all of these reciprocal functions. And in the case of both of these examples, the x-axis and the y-axis are both asymptotes. So some verticals and some horizontal asymptotes going on. So again, this is kind of looking at the even and odd function. This would be an even function. That is what happens when your f of negative x is the same thing as your given function, f of x. And then we also can state that it has that y-axis symmetry. So whatever's happening on the left-hand side is mirrored over to the right-hand side. Now, those are your basic reciprocal functions. We're going to look at transforming those using those same ways of shifting left and right and up and down, and some stretches and shrinks that we've already done. So let's look at an example. It says using transformations to graph a rational function. So it says use the graph of f of x is equal to 1 over x to graph g of x is equal to 1 over x plus 2 minus 1. So the original function, our f of x is equal to 1 over x. That is what is on this graph already. That was that first type of example that we looked at in the previous slide, right? We have our given regular function. Now what happens with that given function, we know that we start having those asymptotes. We're going to have this horizontal asymptote that's going to go from our left to right. And what causes that horizontal asymptote is when you are looking at, I'm sorry, I lost my page. When you're looking at the bottom power is bigger than the top power, that's what gives us a horizontal asymptote at 0. That was in the previous lesson, so if you missed it, you might want to go back and check that out. What happens with our vertical asymptote, this vertical asymptote is going to come by taking this denominator and setting that equal to 0 to find those exclusions, right? So if I were to set x is equal to 0, that means x cannot be equal to 0. That's what makes that vertical asymptote that we have there, right? So the horizontal came from the fact that the bottom has a bigger degree. That's what gives us that horizontal asymptote at 0. And that vertical asymptote came from setting the denominator equal to 0 to find out those exclusions. So that vertical asymptote has an x is equal to 0. Then it says from there that we'll identify 2 points and the asymptotes. So I started with the asymptotes, no biggie. Let's find 2 points. 2 points means to look at that graph. I feel like I need a new color. And identify some points that are easy. So the easiest points to kind of identify is going to be when we're over at 1, we're up at 1. We're going to have the ordered pair 1, 1. And then when we're over at -1 and down at -1, that's going to be another ordered pair that's going to be easy. And all that's really coming from is going back up to that original graph and looking at kind of some easy points. These are going to be the easy points to be able to translate. We're going to take those points and we can shift them left and right and shift them up and down pretty easily. Same thing with the other function when we get there, 1, 1 and -1, 1. Those are going to kind of be your go-to points that you're going to use as your shifting points. So let's continue on. Once we kind of identified some of those pieces, right, we were able to identify 2 points that we're going to be able to move, and then we also identified those asymptotes. It says that the graph is going to shift how many units in what direction. So we need to look at what's going to happen with our shifts. Now, if you remember back to transformations, we talked about something going on with the x. What's going on with the x? We had to stick that inside of our head and we had to think about it. That's going to tell us how we shift from left to right. Now, if I have a +2, remember we had to stick it in our head and think about it, that's going to do opposite of what we think. So if we have a +2, what direction do you think it's going to move? It's going to move to the left 2 spaces. And how else could you remember that? Take that x plus 2, set it equal to 0. That means x would equal -2, which means that it cannot equal -2 because that's where that asymptote is going to be located. So it's going to shift that asymptote over to the left 2 spaces. So if I had originally, I had that my vertical asymptote was through 0, all that's going to do is it's going to take that and it's going to shift it to the left 1, 2 spaces, and it's going to drop it down. All right. What about this this -1 that's happening over here? What do we remember about our transformations with a -1? Well, that's going to shift it up and down. Which direction are we going? That's going to shift it down 1 unit. Which means that if I had that horizontal asymptote, and I were to take that, I'm going to grab some of my green with it, that's okay. I'm going to take that, I'm going to do what? I'm going to just shift this down 1 space. And now my horizontal asymptote and my vertical asymptotes have shifted. So our vertical asymptote would have shifted to an x was equal to a -2. So I'm going to go back and fill that in. Vertical asymptote was a -2, and then we said that our horizontal asymptote is going to be at that y is equal to, sorry, not +1, -1. So let's see, the graph, because our asymptotes are shifting, we shifted to the left 2 places. We can say that the graph is going to shift. We had 2 places or 2 units to the left. And if we move 2 units to the left, that means that we are going to subtract 2 from each x coordinate. And so our vertical asymptote is now at that x is equal to -2. And we will shift our ordered pairs in a moment. I'm going to finish filling in the rest of these words. It then says that the graph is going to shift. Well, where did we go? We also shifted it 1 unit down. And that means that if we're going down, that means, again, we're going to use some subtraction. That means we're going to subtract 1 unit from each of the y coordinates. And we said that the horizontal asymptote is now going to be at that -1. So if I take those two ordered pairs that we used as kind of our points that we're going to shift around, we had the ordered pair 1, 1, and we had the ordered pair -1, -1. And all we're going to do now is we are going to do these two things. We're going to subtract 2 from the x coordinate, and then we are going to subtract 1 from the y coordinate. So if I subtract 2 from the x coordinate, that means 1 take away 2 takes us to a -1. And if I take a +1 value and we have to subtract 1 from the y coordinate, 1 take away 1 is going to land us at 0. If I started with an x value of -1, we said we're going to subtract 2. So -1 minus 2 is going to give us a -3. And then if I take my y value and I'm going to subtract 1 from that, a -1 take away 1 is going to take us to a -2. So that means our points are going to shift as well. So if you want to kind of even think about it that way, if I take that ordered pair 1, 1 that I started with, I'm going to shift it to the right, to the left 2 places, and then I'm going down 1 place. So where's that going to land? That's going to land at -1, 0. If I take my ordered pair that would have started at this -1, -1, we're going to shift it over 2 spaces, and we're going to shift it down 1 space. And where does that land? That lands at that -3, -2. All right, so that I just kind of drew in there to kind of show you how that's shifting. You don't need to have that as part of your graph because that might end up eventually confusing you. So I'm going to take this and just kind of do a little deleting. Now, what's that going to look like in terms of our graph now? We are going to have, I know it kind of looks like a lot of stuff going on. We are going to have this curve that's going to approach the y-axis, come down and hit that point, and then it's going to try to get as far to, not the y-axis, but that vertical asymptote, and it's going to try to get as close to that horizontal asymptote as possible. And then same thing with our other piece. It's going to try to get as close to that vertical asymptote as possible, come up here, hit that point, and then it's going to go off to that left-hand side and try to approach that horizontal asymptote as much as it can. So that's with our graphing. All we're doing is transformations, which is what we did in the last chapter anyway. All right. We are going to go through our strategies for graphing rational functions. So what are the things that we're going to do? There's going to be 7 steps we're going to follow. I know 7's kind of a lot. So our strategies for graphing a rational function, it says the following strategy can be used to graph f of x is equal to p of x over q of x, where p and q are polynomial functions with no common factors. Remember, if they had those common factors, that's where we were talking about those holes that might be located in the graph versus a vertical asymptote. So step number 1, it says to determine whether the graph of f has symmetry. That goes all the way back to chapter 1, right? F of -x is equal to f of x, has that y-axis symmetry. That means it's an even function. F of -x equals the opposite of f of x is where we have that origin symmetry. Step 2, find the y-intercept if there is one, because remember sometimes we have vertical asymptotes at that. So it says find the y-intercept by evaluating f of 0. Plug in a 0 for x to solve for a y-intercept. Step 3 says to find an x-intercept if there are any by solving the equation p of x is equal to 0. So why are we just looking at p of x, right? P of x is the numerator. If you think about it, if we're finding an x-intercept, that means we set y equal to 0. If y is equal to 0, we have 0 is equal to p of x divided by q of x. Now, if I undo a divide by q of x by multiplying that over with the 0, that's going to leave us with 0 is equal to p of x. That's why they say you just have to set the numerator equal to 0 to find x-intercepts, because once you undo that denominator over to the other side, it becomes a 0. Step number 4. it says to find any vertical asymptotes by solving the equation q of x is equal to 0. Remember, q of x in that case, that's the denominator. If you set the denominator equal to 0, that's going to tell you what those exclusions from the domain are, which tells us what those vertical asymptotes are. Step 5, it says to find the horizontal asymptotes, if there are any, by using the rule for determining the horizontal asymptote of a rational function. That was where we were comparing the top of the top denominator, You are looking at the degree of the top compared to the degree of the bottom. So if the top degree is greater than the bottom degree, you have no asymptote. If the top is equal to the bottom, you have that ratio of the leading coefficients. Again, this was in yesterday's notes, slightly written differently. If the top was less than the bottom, that is where you have a y is equal to 0 asymptote. Step number 6 says to plot at least one point between and beyond each x-intercept and vertical asymptote. That was kind of where we took those ordered pairs 1, 1 and -1, -1 in the case of the last example, and we were able to kind of shift those to see what was going on with that. And then step number 7 says to use the information obtained previously to graph the function between and beyond the vertical asymptotes. So always make sure, sometimes you might end up with 2 vertical asymptotes. You might also have to find something in the middle, and then looking at those behaviors, to what infinities are they heading towards? Are they going to positive infinity or are they going to negative infinity? We're going to try one. So for example, it says to graph a rational function, f of x is equal to 3x minus 3 divided by x minus 2. So it says to determine the symmetry. So if we find f of negative x, all we're going to do is go about plugging in the negative x wherever we see x. So that means we are taking a 3 times a negative x minus 3 over a negative x minus 2. And if I simplify that down, we end up with a negative 3x minus 3 divided by a negative x with a minus 2. Is that equal to what we started with? Do we have y-axis symmetry or origin symmetry? Well, in this case, we're not going to have no y-axis symmetry because that is not equal to my original function. It's not even. Well, what happens if I take the opposite of f of x? Let's see if that equals one of those things. That means I'd have the opposite of my original function, 3x minus 3 over x minus 2, which is going to give us, that kind of negative gets distributed out. We have a negative 3x, it'd be a plus 3, and we'd have a negative x and a plus 2. Is that equal to either of what we already started with? No. So that means we're not going to have origin symmetry. So no origin symmetry. So it doesn't look like we have any of those symmetries. We move on to step 2. Step 2, find the y-intercept. That means we're evaluating f of 0. That means everywhere we see x, we plug in 0. So that means we have a 3 times a 0 minus 3. And we have a 0 take away 2. 0 minus 3, negative 3. 0 take away 2 is the negative 2, which gives us a positive 3 halves, which gives us an ordered pair. When x is equal to 0, we have a y-intercept of 1.5 or 3 halves. Step number 3. It says to find the x-intercepts. Now remember, they said you just have to take the top and set it equal to 0. So if we solve that down, we have 3x is equal to 3, which means that x is equal to 1. So if I have a y-intercept an x-intercept, I have over at 1, up and down 0. So there's another ordered pair I get to put on my graph. Finding vertical asymptotes, that's where we're going to set that denominator equal to 0 to find out those exclusions. So in that case, if we solve to get x by itself, we end up with x is equal to 2, which means that that's where our vertical asymptote is going to be located. So it's going to be that dashed vertical line. Step 5, find your horizontal asymptotes. So take a look. It wants to know, it says the numerator and the denominator of f have the same degree. right? We have a 3x over x. They have the same degree, the same power. That means that we're just going to take the ratio of the numerator's leading coefficient to the denominator's leading coefficient, which is going to give us a horizontal asymptote at y is equal to 3. It wants us to find some extra points in between and beyond. So it says to plot some points between and beyond each x-intercept and vertical asymptote. So if you think about it, we have said the x-intercept, what do we have? Our x-intercept was 1, 0. Our y-intercept, what do we have that? Our y-intercept was at 0 and 1.5 or 0, 3/2. So we know we're going to have, let's see what else we had. We had some vertical and horizontal asymptotes. Let's start putting those on there too. We have a vertical asymptote at x is equal to 2. So if I go and I find my vertical asymptote was x is equal to 2, and my horizontal asymptote, we had our y was equal to 3. If I were to draw some of those in, x value of 2, so we're going to have, not perfect, that's really terrible. We have a horizontal asymptote at 3. We have, let's see, we have an x-intercept at 1, 0. We have a y-intercept at 0, 1.5. So about here. Now we can kind of figure out what's happening on the left-hand side of that vertical asymptote. And we probably have an assumption as to what's happening on the right-hand side of that vertical asymptote. But what they would recommend doing is, let's throw a couple extra points in here. So if we were to take a -1 and evaluate it, let's try a +1/2. We could try a +1.5, a +2.5, a +3 to kind of start getting some of these things. And just to save a little bit of time, you're just going to take and throw in these numbers for x and solve. So 3 times a -1 minus 3, and then a -1 minus 2. We'd end up with a +2. You can throw it in your calculator, check it out later if you'd like. So at -1, we'd be at a +2. If we were at a +1/2, let's see, +1/2, I'm just going to give you some numbers. We'd end up at 1. So at a +1/2, we'd end up at 1. That kind of falls in between here a little bit. If we're at 1.5, that's going to give us a -3. So if we're at 1.5, it's going to give us a -3. If we're at 2.5, it's going to give us a +9. At 2.5, we're going to be up at +9. At 3, 3 times 3, 9, that's 6 over 1, we'd end up with 6. So if we're over at +3, we're up at 6. You see how that behavior is starting to occur? It's obviously clear on that left-hand side what that's doing. And we can see that the other points are starting to fall into the same kind of idea as to what we would expect to happen. So that's going through and graphing or following your 7 steps, because step 7 is to graph the function.